So hello everyone, welcome to another Stark at Home episode. My first question always is, can you hear us? Can you see us? You're supposed to see three faces. So please type in the chat, can you hear us well? I'll just wait for someone to type. I guess there's some delay going on. Cool. Thank you, Peter. Okay. There's always a delay. So thank you, Tony and Patrick. Okay. So I'm Eli Ben Sasson, co-founder, president at StarkWare. I am joined by, this episode is about recursion. So we're going to have a recursively applied naming scheme here. So we have one Shahar, and then recursively we have another Shahar. So we have Shahar Papini. Maybe you can wave. So Shahar Papini, Cairo co-creator at StarkWare. And we have Shahar Samocha, another Shahar, software engineer at StarkWare. And together they've been leading the teams that have been working on making recursive STARKs, something that is now working in production. And there were already a bunch of talks about recursion and recursive proving and recursive STARKs. And this episode is going to be about talking about what it actually means to run a system in production that uses these objects. I want just to start by showing this teaser. I want to share my screen. So I hope you can see this. I'm sharing. So I did a little poll 2.5 hours ago, and I asked how many NFT mints can StarkEx put in a single recursive Stark proof today in production. So 235 people voted. The question was 1 million in a proof, 5 million in a proof, or 10 million in a proof, or what's recursive Stark? And what you see is that 10 million opted for 37% opted for 10 million, whereas 35% opted for saying, what's a recursive Stark? So let me now stop sharing and go back. And most of this will be, so I'll leave you with this cliffhanger. We'll get to hear later on from the recursive Shahar the answer to this riddle. Before we talk about recursion and the technical stuff, I do want to say just a few words about the whole situation in cryptoverse with this FTX catastrophe. And just because it's on everyone's minds, at least, okay, among our listeners, there are folks who come from the academic world and maybe don't even know what FTX is and so on. But probably there's a lot of folks that actually do follow cryptocurrencies, and maybe some of them have even been affected by this meltdown. So I want to say, so just briefly, there was this exchange called FTX, which asked users to send assets to be custodied with it under the assumption that those assets are going to be staying there and always there because they're yours. And then by some machination, poof, those tokens aren't there anymore. And a lot of users have lost a lot of funds. And that's very, very sad and tragic and probably criminal and very dramatic in our space. So first of all, my heart and our hearts go out to all those who were affected by this. This is horrible. I've been in the crypto world since 2013, and this is the most astonishing, tragic thing I've seen so far in this space. And it's definitely rattling everyone up. Now, when people look at the solutions and the problems, so you have to remember that this is a result of leaving custody over your tokens with another third party. And it may be very convenient and pleasant, but it's also very risky. The technologies that we've been building for nearly 5 years since the start and have been deployed already for the past 2.5 years prevent third parties from doing these things. Everything on the StarkEx system has been and will be self-custodied, which means that the operators of systems that use StarkEx technology cannot take tokens locked there and do anything with them. They have to provide Stark proofs, and the Stark proofs have to attest to the integrity of the computation and to the consent of the users to do whatever they want to do with them through the programs that are constraining them. So this cannot happen on systems that are using StarkEx technology. And people are now saying, oh, what went wrong and how could things be done better? So things can be done better if people move to self-custody. There's enough scale and enough convenience of using these systems today that such things could be prevented. And I hope that more platforms embrace these kinds of technologies, self-custody technologies, so that users will have a good experience but won't experience these catastrophes. So that's just a statement about that. And now I want to move on to talk about recursion. So what is Stark at Home? For those who are new here, it is a venue for talking informally about things that involve very deep technology and very deep math related to Starks. So there will be no formal definitions, no theorems, no proofs, but this will talk about very deep and challenging things. If you once in a while will pause for questions. So if you want, please use the Ask a Question button. So I'll just give an example. Here's a question. And you can just type it. It's the Ask a Question button. It's very hard to keep track of the chat. So like I saw that some people were asking some things. It's going to be very hard. If you have a question, please use the questions and answers. So without further ado, let us start talking about recursion. And I'm going to ask Shahar Papini, 35% or so from the people polled said that they don't understand what recursive STARKs are. So what the hell are we even talking about here?
Hi there, can you hear me? Yeah, I hope you can hear me. Can you hear me? Guys, Eli?
I can hear you, but I want maybe someone from the chat just to make sure.
I see. No, I guess they'll hear me. Okay, so to understand what's recursive STARKs or recursive proving in general, let's have a quick review about STARKs and proving without the recursive. When we are talking about STARKs, we are talking about proof systems for computational integrity. Basically, you have some computation that you did want to do yourself. Maybe it's a long computation, maybe it's computing some kind of hash, or maybe a transaction. And you want to take this computation and make a proof, a short proof, such that you can give this proof to another guy, let's call him verifier, and he can look at this proof and very fast verify that this proof is correct and understand that the computation I did and the result I got is correct. So for example, I can do some very complicated hash, and my proof would say that the hash of 1 is 17, and then the verifier can know with a very high degree of certainty that indeed the hash of 1 is 17 without performing all the intensive computation on his own. So that is the proof system for computational integrity. And Stark is a specific proof system that does it, and this is what we are using at StarkWare. And maybe we'll dive a bit more into what exactly we have inside this protocol, but that's for later. So recursive STARKs says something very simple. Okay, we can take basically any computation we want and prove it. And then we can give it to a verifier, and the verifier needs to run some verification process, and then yeah, it's okay. So what if we take this verification process that is already a lot shorter than the proving time, and we make a proof for that? So if I have this big computation of a hash, I'll make a proof of that, and then I'll create another proof for the verification of this proof. And then I can repeat. I take the computation of the verification of this second proof and make a third proof and a fourth proof, and so on. The benefits we get from this is making it shorter and shorter, or being able to batch more computations together. So let's say the first computation had a million steps, and then the verification is a lot cheaper. Maybe it's just 1,000 steps, and then maybe I can take like 10 of these and still get a very short computation and make proof of that, and then I'll get shorter one, and then batch more of these. So I might have this big tree of batching of computations, and basically I'll get a very, very, very short proof that actually proves a lot of computation. And this is good, especially for the use case of roll-ups, blockchains in general, because it's very expensive to run computations on blockchains. So we basically take a very big computation and make a very, very short proof of a lot of computation. And this computation is the only thing that needs to run on the blockchain. So it should be very, very cheap. This is the essential of recursive STARKs. Someone wants to add anything? You're on mute, Eli.
Yeah, maybe I'll just rephrase what's going on. So you have when you have a Stark proving system, it turns out that the verifying a proof is done by computation, but the computation is exponentially smaller than what you attest to. Okay, so you start with a long computation, and to verify it, you run a different computation, one that is very short. So now you can attest to having running this shorter computation. You could do this again and again, not ad infinitum. There are actually very significant security, cryptography, and math questions that unpacking them and explaining them will be the topic of a future episode. We're not going to touch on it at all here, but it is a very interesting math and cryptography question that we're not dealing with here. So that's essentially what Recursion gives you. And now I want to ask Shahar Samocha to tell us what is, can you give us, first of all, can you answer this question, this polling question, how many mints can we do or could we do of NFTs before we had recursive proving, and how many can we do today? And can you tell us a little bit about the dramatic effect of these numbers in production today as we use them?
Hi, yeah. So basically in the old Sharp system, we could batch like 600,000 mints and generate a single Stark proof of it and verify it directly in the blockchain, as Shahar said, very cheaply. Now with the recursive Stark, later on I explain what it is, we can do 10 million mints in a single Stark proof, which induces a very minimal cost per transaction on chain. So I'll start with what Sharp is. So Sharp, which stands for Shared Prover, is a system that can get multiple logics written in Cairo and generate a combined Stark proof to verify all of it together. The problem is that we want to generate the proof as large as we can because, as I said before, that induces the lowest price per transaction. But that is also cost us in latency because we need to wait for this whole lot of transactions and generate the Stark proof for such long computation is also expolinear, like over the linear and polylogarithmic in that. And that's costly when you want to prove such large computation. Using the recursive Stark feature that Shahar Papini explained before, we can now take multiple batches of different transactions, like where each of them is proving different logic, generate a Stark proof for each one of them in parallel, and later on we can combine them into something that will look like a tree, where each inner node is the proof of the verification of its child nodes, and do all this computation off-chain, and only the root of the tree is being sending to the blockchain in order to verify the entire tree. So with this feature, we are now able to verify like 10 million mints in a single batch, in a single Stark proof that is sending to the blockchain.
So can you give us some numbers on like amortized cost per mint previously, and how much like amortized gas per mint now in the new system? How does it look like?
Yeah, so as we said, the verification of the proof is always logarithmic in the execution length. So when we verify the proof on chain, which is a proof of proofs of proofs, it only costs us like 5 million gas to do it. So if before we could, we had a capacity of like 600,000 mints, and it cost us like 6 million gas, it was, if I'm not mistaken, like 10 gas per mint. And now we can do 10 million with the same price, because the last verifier job is on a pretty short computation. It's of other verification. So the gas cost is stayed the same, but now we are able to prove a lot more mints or any computation.
Yeah, if I got the math right, so if it's roughly 5 million gas that covers 10 million mints, it means that the amortized gas per mint is roughly half a gas, so like sub-unit gas per mint of NFT. I think that on layer 1, it's an average of roughly 100,000 gas per mint of NFTs if you do a straight up NFT on Ethereum. I want to still stick with the numbers and configurations and so on. So can you say, so now we have much greater proofs thanks to using this recursive structure. What are we, like, everything in life is a trade-off, right? So there are some trade-offs here, right? Some things get better, some things get a little bit worse, some things you change configurations of the, computation, memory, things like that. Can you tell us a little bit about how things change from when moving from like a single prover to a much larger proof with recursive proving?
Yeah, so to our surprise, this feature was induced as an improvement in all of the aspects. Like usually we have a trade-off between latency and cost. Like as long as we can allow a more latency for the transactions, we can generate a larger tree of recursive proofs and essentially have more transactions in the last single proof going to the blockchain. But now, using the recursive feature, we can prove all the layers in the same tree, all the nodes in the same layer of the tree in parallel. So actually the latency is much lower than before. Like proving the 600,000 mints in the old sharp system took us something like 10 hours of proving time. And now using the parallelism of the prover, we can prove the 10 million in something like 6 hours, which is much lower. also the cost per transaction is lower, as we said before. One last improvement, this is very surprising, is that also the off-chain cost of the proving time is now lower. Like the total proven work is now bigger because now we have to also prove the verification jobs, which combined each time the child nodes of the tree. But now we are using much smaller servers from the servers we had to use before. Like generating those giant proofs needed us to use like super machines with tons of memory and CPU, and now we can use like machines which are cheaper, and also because the proving time each time is not so long, we also were able to use spot instances, which make the off-chain price very low in comparison to before.
Okay, maybe let's pause to answer a few questions, and then we'll go on to like getting a bit deeper understanding of how what actually is being proved and verified recursively. What are the different modules that the verifier is checking and how this thing works, and then also addressing how we can tweak these different modules and what will happen if we do so. So that's where we're heading towards, and we'll also talk a little bit about some specific numbers and layouts and how actually things are in both at the leaves of this recursive thing, how actually the computation looks like. But let's pause here to take a few questions. So and please use the ask a question button. So question number 1, is there a limit in principle to the number of recursive steps that you can do? Who wants to answer this?
I mean, theoretically, it depends on the soundness. I think that, Eli, do you know what? I don't think we know of the concrete analysis of the soundness for a large number of steps, but it seems safe to assume that for low number of recursion steps, it is safe. But to really answer how many we can do, we'll need to analyze it a bit more theoretically.
I want to try answering this. Yeah, Shahar, do you also want to add to it?
I want to say that the soundness effect on it is like work in progress that we are doing now together with Alessandro Chiesa, Elon Yogev, and Zig1. And we are now only checking how the soundness is affected by the recursive feature.
Okay, so I want to add to that definitely there are limits. We know that, and this is true for all proving systems, we know that no matter what you do, in the end, the amount of work the verifier has to do for checking a proof cannot be less than logarithmic in the total number of steps of computation that the prover is doing. So you cannot go below log t, where t is the overall number of steps. This is a mathematical impossibility. A lot of would break math if that could happen. So we know, but log is a very small number, right? If log of a tera is just 40, so it's not a very large number, and we don't know how to get proofs of 40 bits long anytime soon. So the theoretical analysis, which is just being started to work on, as Shahar pointed out, will give us a more concrete answer. There are limits, and definitely you can't do it indefinitely and to all depths without. It would work, but it would harm soundness in ways that will quantify and report. But that's a very good question. Okay, next question. Hello. Why we should choose StarkNet even if it has low speed of transactions and it is not an EVM-based blockchain, much longer addresses? My user's experience was not absolutely positive due to this case. Process of bridging ETH from ETH mainnet to StarkNet also took some time, 1 to 2 hours. Thanks. It's not a topic. I don't want to avoid this question. It's a terrific question for one of the community calls on StarkNet. It's not related to recursion. very briefly, I'll answer that. We call StarkNet Alpha for a good reason, because it is still in alpha. It still needs improvement, and in particular, it needs improvement in the throughput. We'll get there. We'll get there very quickly, but it's not the topic of this. It's not related to recursion. I mean, not directly related to recursion. I don't know, Shahar, do you want to add anything to that?
No.
I just don't think that the recursion O sharp is the limitation that what limits StarkNet, or those things that you mentioned.
Okay. Sorry, Shahar, you wanted to say another thing?
Yeah, just like Shahar Samocha said, it's not a limit of the technology. It's a temporary limitation of a system that I hope will be resolved in the next few months. Less, maybe, yeah.
Okay. Another question, is that Blake too? For I'll just say very briefly, things that are not related to recursion in this talk, we won't be answering. So in particular, someone's asking about tokenomics. Sorry, it's a very interesting topic. We wrote some blogs. It's not related to recursion, so I'll just we're not going to answer that question. Similar other things that are not related. We'll focus on things that are related to recursion. So here's a terrific question: is that Blake 2 or Fiat Shamir and Peterson for Merkle trees? And I know later on we'll dive into it in much more detail, but maybe just answer briefly, and then we'll give more details later.
Okay, briefly, it's we are using Blake 2 for the commitment trees right now, and the Fiat Shamir. We are using Pearson on part of the Fiat Shamir, and we have right now plans to split the commitment between Blake and Pedersen. But I'll dive into it later.
Okay. Here's a terrific question. I think, let's see. How is that 10 million number, I guess for mints, supported by the storage capabilities of ZK Rollup? Or isn't it like Plasma? I guess, or is it like Plasma? I think Plasma is something where, there's Rollup and Validium. Okay, so yeah. What's the effect of data availability on this? How do you figure it in?
Right now, the mints, if you're working in Validium mode, then it shouldn't matter. If you're using some kind of cheap data availability solution that we might have several options for StarkNet, then it's also not a big issue. If you want to save it on storage like on StarkNet, then it's going to cost you call data on Ethereum. That's basically it.
Okay. Next question. How deep is the recursion tree in practice? There's another question about basically speed of mainnet StarkNet. Again, not this topic. We addressed it briefly, so I'm going to delete it. How deep is the recursion tree in practice in order to have reasonable time to finality?
I'll answer. So now in mainnet, we have a limit of 128 leaves in this tree. We said that if it was a full binary tree, it has 7 layers. So we have 7 recursive steps, and that could be achieved like in 6 hours of proving, even less.
Okay, and I see a comment on this. So Professor Daniel Ogo is asking, can the question be complemented by a discussion of parallelism versus tree? I'm not sure I understand exactly what you mean. Maybe you can elaborate, but like, I think the tree is, so we do process it layer by layer. And then you have parallelism on each one of these layers. So you have 128 machines running at the base layer, basically in parallel. And then, it would be logarithmic. The latency is logarithmic in the depth. I mean, Shahar, correct me if I'm wrong.
Also, I think Shahar Samocha can say a lot about it, but basically it's like an online scheduling problem. I'd say that we get each time step, maybe we have this new job and we can start working on it in parallel and then maybe combine some together. So there is parallelism, and it's involved with online scheduling.
Shahar Samocha, do you want to elaborate on that?
It sounds also very simple, like when you say that you got all the 128 jobs in the same time, but the truth is that they can come in different times. The scheduler can't know at which time he gets another job or if he doesn't get it anymore soon. So the online scheduling problem is pretty tough, and we have to think about how to generate those trees in an optimal way.
Okay, I'll try to explain what I understood, and correct me if I'm wrong. Basically, suppose you had in 1 second all of the information that should occupy these 128 leaves. For instance, you got this huge batch of 10 million mints. Then you would probably pretty quickly allocate them to 128 different machines. They all start working in parallel. But the reality is that there are a variety of reasons in which you would want different leaves to look differently. And this is related, I think, to layouts and things like that, and we'll get to that later. So not all leaves are of the same kind, and they don't get filled in the same rate, the leaves of this recursion tree. And this leads to a scheduling problem that is on top of that of generating the proofs. Did I get it roughly right? Okay. So, and we'll get to that a little bit more, the question of layouts, and that's the next topic. Okay, so question. Say we have a Stark proof that has no ZK. Then we have a recursive Stark proof with ZK on the no ZK Stark proof. Does it imply that the witness of the no ZK Stark proof is also hidden? I think so. So it's a trick question, but like if you have a ZK that recursively proves something about a non-ZK, my limited CPU on the line thinking says that yes, you will get the whole thing to be ZK because like the last one hides it. The more interesting thing is what if you have non-ZK applied to ZK? I guess this one hides it. So maybe ZK anywhere along the route hides it. Even more interesting is what do you have two non-ZK things? Do you get privacy? And I think you'll probably get, practically speaking, pretty decent privacy, but not provable ZK, I think. I don't know what's Shahar's. What's your gut feeling?
Yeah, my intuition is that you will get ZK, but that is all I can offer.
Yeah, but it's a good question. Maybe someone should write a paper on it, like ZK with non-ZK. What happens? Okay, is recursion a feature you expect Snark-based proving systems to achieve as well, if they haven't already? Are Starks better suited for recursion in some way? I'll start by answering this. So any proof system that has succinct verification, where not even succinct, lower total time to verify than it is to run the computation, you can apply it recursively and sort of compress things. And Snarks had recursion even before, at least academically, even before Starks had them. So, I mean, Alessandro and I and a bunch of other co-authors probably 5 or 7 years ago wrote an academic paper on recursive Snarks, and it's certainly implemented, I believe, in the Mina protocol, and I think Halo 2, which I think is either now already turned on in Zcash or will be. So there are a lot of ways to do recursion, and yeah, Snark recursion works as well. There are differences, many differences, and again, this is not a topic we'll go into now, on like the kind of extractability assumptions and the soundness and how you think about it between Snarks and Starks. But the short answer is yes, you can get it on other systems as well. Okay, I think let's take just one more question and then just move on. Not because they're not good questions, just because. Okay, what is another potential use case for recursion other than NFT minting? So I'll just say this is a really terrific question. We'll get to all kinds of very interesting use cases soon. So let's not answer it now. but it's a really good question. And now let's move on to the next topic. So, Shahar Papini, what exactly is being, what kind of computation is being executed when you generate a proof for the fact that you verified another proof? What exactly are you executing there, and what are the components that are involved?
Yeah, diving into all the details would take a lot longer than we have. I'll try to give a brief overview of how a Stark verification looks like. Just I'll repeat what I said before. Basically, recursion is just that we need to prove the computation of the verification, which in our case is Stark verification. And the Stark verification has a few components. I think the easiest is verifying Merkle commitments. So we have these Merkle trees inside the proof that we are committing on evaluations of things. But basically, a big part of the code and a very large part of the computation itself, in terms of how many steps we need, is verifying Merkle commitments, which basically means verifying a lot of hashes, of hash chains. So this is one part, the commitments. Another part is what we call Fry. Fry is a tool that Stark uses. It uses it for low degree testing. Basically, we have this commitment on an evaluation of this polynomial, and the Fry protocol, using repeated commitment revealing and decommitments and some algebraic computations, manages to prove that this commitment is close to a low degree polynomial, which is a big part of Stark. So this is the Fry that caused a lot of commitment validations and these algebraic formulas inside. A third part is the error itself, which is stands for algebraic intermediate representation. Basically, the first computation needs to be stated in terms of polynomials or some algebraic representation. We call this error, and the computation part it takes inside the verification is basically evaluating some polynomial that we all agree upon on a few points inside this prime field. And in the recursion, we use the same prime field for the arithmetization of the original problem and the arithmetization of the verification. So it's cheap to evaluate this polynomial, relatively cheap. So like I said, three parts: Merkle commitment verification, the Fry algorithm for low degree testing, and the AIR, which is arithmetic intermediate representation, basically evaluating polynomial at few steps. And there is a lot of logic code for glue code for everything together. Now I want to say just quickly that although Starks get this arithmetization, which means you need to express your computation in polynomials, it would be very, very, very hard to express this kind of computation, this Stark verifier computation. It would be hard to express it in raw polynomials, and that is why we are using Cairo. Cairo is this general machine we have, and we can express general computation in Cairo, and we have this single polynomial that can verify any Stark any Cairo program. So basically, what we actually are doing, we're not taking a Stark verifier and making polynomials for it. we're taking a Stark verifier and just writing it in high-level Cairo language. And then we automatically get the recursion because we already know how to prove any Cairo computation. Yeah.
So now let's start having fun with like playing around with these different modules that are all of them already written in Cairo and run and prove. Suppose when we recurse on things like the Cairo virtual machine, and that's what we have right now. But what happens if we want a different virtual machine? Suppose tomorrow we want to throw out the virtual machine that is Cairo and prove that we correctly executed, I don't know, x86 or some LLVM or the EVM, which is a very hot topic that everyone wants to do, or one of these things. What would you need to modify in the proving that you ran a verifier in order to make that work? How hard would it be?
Yeah, so first of all, if any of you wants to look at the recursion code, which is basically the Stark verifier written in Cairo, you can see it. It's open today in our Cairo Lang repo. It's under Stark verifier. You can look at it. And basically, it's a modular in the air. If you look at the code, you can even take it yourself and have fun with it. Basically, you have all the air components in one place, and you can just replace it. There are a few files, but mostly there is this big file of the polynomial and some parameters. So you can basically plug in another air to prove, and Stark verifier will prove this air. I'd say that we at StarkWare have this framework to auto-generate some of this code. This is not open source. It's something we have, so it's even easier for us. But it's still easy to just change the polynomial if you know what errors are and what the polynomial you want. You can just change it and run it. And by the way, you can probably just take it today and run recursion maybe on StarkNet, and maybe when we want to do L3s, this will probably be the same code. Maybe I'm getting ahead of myself here. Yeah.
Okay, now I want to ask Shahar Samocha, what would happen if we would change so when we recursively prove that we verified a Stark, a lot of the work goes into verifying that things were properly committed by Merkle trees and then opened in the correct way, and that depends on the particular hash function. So my question now to you, Shahar Samocha, is how much are we spending in terms of our proving and verification on dealing with these commitment schemes? What are they now? Like, which hashes are they, and what could you replace them in the future, and what would it lead to?
Yeah, I was muted. So as Shahar said before, the prover has to commit on a Merkle tree, which is essentially a binary tree of hashes, and the verifier just sample a few locations of indices of the leaves and check the path from these leaves to the root. So the prover has to compute the entire tree, and the verifier has to check only some path, which is logarithmic of the size of the tree. Yeah, it's like the tree height. Now we were using Blake. Yeah, then let me know if I'm wrong, but I think that we used Blake for the commitment scheme hash, and we were verifying it on Solidity verifier. So it was very good, although the commitment scheme is pretty much the heaviest part of the Stark verification.
I just want to mention that before recursion we used Ketchuk, and in recursion we're using Blake. Yes.
Yeah, so it was Ketchuk, yeah. Okay. Now that we use recursion, we are going to say to send the proof that we generated into a Cairo verifier, like a Stark verifier written in Cairo. And Ketchuk or Blake are not hashes that are friendly to Cairo. So we wanted to make the verification job faster. We need to verify hashes that are Stark friendly, like Peterson hash. The problem is that Peterson hash is not very fast to compute on an x86 machine. So we have a trade-off here for which hash we're using. In the case that if we use a Blake hash, the prover will compute it very fast, but the verification will take very much time. And on the other hand, if we use Peterson hash, the verification will be very fast, but the prover will take a lot of time to compute it. So Kinneret in StarkWare worked on the flexible hash commitment, which is essentially a Merkle tree that is composed of two hash functions. Like the lower levels of the tree are computed Blake hash functions, and the top layers of the tree are Peterson hashes. So now see what's happened. Like in each binary tree, the leaves are the number of leaves are equal to the number of inner nodes. So if we take the last 10 layers and compute Blake hash, it's like we did 1,000 times more Blake hash than Peterson hash when the prover had to compute it. Although on the other hand, when the verifier is going to verify some specific path, on each path that he checks, he sees only 10 layers of Blake hash and a lot of layers of Peterson hash, which makes the verifier very fast. And also the prover had to compute not a lot of Peterson hash. They only check for 1 over 1,000 hashes of the entire tree. So that should very improve our recursive Stark verifier. Yeah. Do you want to add another thing, Shahar?
Yeah, no. So maybe let's answer a few questions, and then talk a little bit about like where this could go next and what are things in the pipeline. So okay. There's a question, what is another potential use case for recursion other than NFT minting? I'll take a first swab at this and say that, first of all, we use the example of NFT minting just as, just one example, but currently already today, so all of the StarkNet transactions alongside the, StarkEx transactions for swapping of ERC20 and transfers and minting and trading of NFTs, they all go into basically recursive proving. So there are a lot of use cases. And we just mentioned a few more. For instance, you could throw out the module of the heir of Cairo, replace it someday with an heir of an x86 or EVM, and basically have recursive proving for those other models of computation. Shahar, do you want to add to that? What other potential use cases?
No, just like you said, like every general computation that goes through Sharp is basically using this. It's not specific to minting.
Okay. Kalman is asking, hey, if using recursive proofs, how much does it make sense to compress unused data at the beginning of the multiple proofs via a commitment scheme and extract the data at the end of it via another proof? If the data is not used during the recursive proofs, it might make sense to make the intermediate proofs smaller. So I think the question is, maybe like if if several cells are being accessed in the middle of the recursive proof, so somehow compressing it so that only at the very end you update. You mentioned all that happened. I'm not sure I fully understood.
I think it's similar to maybe things we are doing in recursion that we have basically some data on the layers, which basically says what are the outputs of our jobs, and we do compress it by just hashing it. And only in the very last layer we decompress it and then send it to the blockchain. So we are doing something very similar, I think. We're not using a commitment scheme, we're just using hash because we need to decompress all of it.
Okay, so a question here. Hello, StarkWare team. Do you have a POAP, a proof of actual attendance and presence for AMA attendees? So the short answer is no. The main thing that you get from showing up to Stark at Home is you get wisdom and knowledge, but no POAPs. Sorry. We're not that kind of project. Okay, so since the Fiat Shamir heuristic degrades security, wouldn't that deterioration compound quickly with the recursions? Yuval is asking. Oh, that's a terrific question. I'll give a first answer and say I don't think it deteriorates quickly. It does deteriorate in ways that are, as Shahar mentioned, both Ziggy and professors Alessandro Chiesa and Elon Yogev and Shahar Samocha are thinking about this. But we don't want to spill the beans. Not all is lost, and we will stand to our security and soundness parameters, but the analysis is underway. I should say, let me just take a step back. The whole question of the concrete soundness, but also the asymptotic and theoretical soundness of recursive proving is very, we don't understand it very well. And I personally often have said that it makes me personally feel a bit queasy because it's like piling all kinds of assumptions on assumptions on assumptions. And it is the sad state of affairs of this whole area. Recursive proving, is like a lot of things in recursion. It's but anyways, we'll once we have the analysis, we'll definitely have another Stark at Home to dive deeper into this. But we, there's nothing we can say at this point. Okay, Tomas asking, hello. How did you design the Peterson hash and why? For example, why did you choose to separate inputs into 4-bit high and low? Shahar Papini, I think that's a question for you.
That does sound like a question for me. I just don't understand it. That's all. Separate inputs into 4-bit high and low. I'm not sure what that means. But by the way, we didn't design the Peterson hash. Maybe you're talking about the Peterson built-in. But I don't remember separating inputs into 4-bit high and low. So I'm not sure how to answer that. Sorry.
Okay, if you can elaborate. Maybe it's some other... Are you sure it's... Okay. I don't know. Next question. So if you can elaborate on that, Thomas, a little bit, what do you mean by... last question. What type of hardware is best suited to run the StarkNet prover versus the verifier? GPU versus FPGA versus ASIC. Oh, in Shahar, do look, there's a pointer to the docs, the Peterson hash function. So maybe, and so, yeah, let's answer this question in the meantime. What type of hardware is best suited to run the StarkNet prover versus the verifier? GPU, I'll take a shot at that. Right now, we're just using x86 machines. Okay. The verifier, this is true of all verifiers in modern proof systems, Starks, Snarks, others. The verifier is very lean, so you can, it doesn't really matter. It runs, if you would run it on an x86 or on any other thing, it would take, a few milliseconds even to verify very large computations. So that's, you really care about the prover. The prover, right now we're running it on x86. You could, each of GPUs, FPGAs, and ASICs will probably give you some extra performance. But like with GPUs, when we looked at it back in the day, the problem was we needed initially very large computations, and GPUs came with very limited memory. And when you do FFTs, you need to use all the memory you can. So it didn't make sense to use GPUs. Now, actually, with recursion, the picture is changing a little bit because you can have these many leaves, and each leaf could have a relatively small computation, maybe something that completely fits inside a GPU, and so it completely changes the game. So maybe GPUs can come back into the picture. We're right now not looking into it just because we're just too over capacity with just other things, but it's a very interesting direction. FPGAs and ASICs, yeah, sure, they could improve, but these are like huge projects that we at StarkWare unfortunately don't have the bandwidth to look into them, but they're really, really terrific things. So I don't know if it answers. So Shahar, do you have an answer for the high bit, low bit?
Yeah. First of all, we wanted to expand the person hash to work not just on field elements, but on 252 bits. It was very convenient in terms of commitments on our trees, but we couldn't just have it be a single the number, the 252 bit number times the point, because then it will be over the curve size. So we need to split it. And the reason we chose to split it into 4 bits, I think, is because the implementation uses some lookup table of size 2 to the 4, 16, and then it made sense to split it like this. This is what I remember. Yeah.
Okay, last question we'll answer for now. And to expand on the previous question, if you're approving multiple transactions, each might have a state diff, and you might not want to push this through all of the recursive proofs, only aggregate at the end. So which one is more economic? Compress the state diffs and expand at the end, or have bigger recursive proofs?
Good question. I think it's both. Yeah, we definitely want to do both. Recursion helps a lot of things, parallelism and latency and the size of the proof. But yeah, if we do too little proofs, then too little leaves, if they're too little, then the compression thing begins to be a problem. But so we don't want too little leaves. It's like an optimization problem.
Wait, why? I thought that right, if you know that you have like all of these trains, oh, okay, I see. Like if you knew all of the data in advance and you have it there, then maybe like just, if you do things sequentially, you could say, here's a hash of, let's say, a diff file, and, you collect like hashes of diff files, and maybe just at the very end, you prove that all of these diff files are correct, and here's the very last one.
Yeah, I mean, if we are doing small leaves, and then we need to express the state diff over this leaf. If we had a big proof, a lot of the state diffs wouldn't even exist at all because they would overwrite each other. But when we do small leaves, we need to somewhere compress all these state diffs. It adds some computation. Not sure if it's very significant.
Yeah, Shahar Samocha, please.
Yeah, maybe it's a good time to mention the applicative shop that we want.
Yeah, please.
To have. Yeah, so there's a few. We didn't start to work about it yet, but the idea is to use applicative shop. It means that we could get a very large computation, and then the shop system itself would split it into multiple slices of that big batch, prove it recursively using our recursive feature, and then before sending it to the blockchain with all the stages, compress it back again to the single batch, and then benefit both from the parallel computation and the one state diff for all the computation itself.
Okay, so now we're towards the end of our of this episode, and I think just briefly, let's talk. So far, when we described recursion, we were talking mostly about its effect on like larger proofs and smaller latency. But let's touch on two slightly more exotic features that could be also benefiting from it. And I'll let each one of the Shahars pick who wants to speak about what. One is like better privacy, and the other is layer 3s. So, and we'll speak a little bit about each one of them, and then we'll call it a day. I mean, answer some questions and call it a day. So who wants to speak about better privacy? Who wants to speak about L3s? Or if there's something else that you think is like really funky that we haven't discussed so far, then please talk about that instead.
I think we can start with this. Better privacy is... you could probably use recursion Okay, I think L3 is better to talk about first, because then we can use it to talk about privacy. L3 is like taking StarkNet, and like StarkNet is roll up that post proofs to Ethereum. Then we can have an L3 that is some kind of its own app or something that posts a proof to StarkNet. So basically, you would have some kind of StarkNet contract that actually calls the Stark verifier, doing the same thing as Recursion and verifying proofs. And we could have, I don't know, an exchange that doesn't post all of its traffic onto StarkNet, and maybe it has a gigantic order book, but only in its own some kind of semi-blockchain or app chain, and only posts proofs of its state change and some kind of interoperability to StarkNet. So this is one thing that the Recursion allows. And note that these kind of apps could be private, could be ZK. They could use ZK proofs, and the verifier could verify these ZK proofs, and then you got ZK on top of StarkNet if users want to have zero knowledge on top of it. It doesn't have to be L3. You can just verify anything. If you write a contract and use the Stark verifier, then you can just verify ZK proofs for anything. That's my 2 cents.
Shahar Samocha, anything funky we haven't mentioned? Either dynamic layouts or privacy. What do you want to?
I don't know what else to say about privacy. Like, this is what I know. Maybe we could talk about some complex circuits that we want to prove on chain. Like,
Yes.
assume that we have a very complex built-in that we would like to prove on chain. I don't know, for some very complex hash or something like that. And then the verifier should know the circuit itself in order to verify it in some sense. But if the circle is too big, that wouldn't be possible on Ethereum L1. So using the recursive feature by itself, we could take this complex logic and verify it using our Cairo verifier, and then take the verification proof and verify it directly on chain. So the recursive feature also enables us to use very complex circuits as built-ins in the Sharp system.
Yeah, I want to expand on this a bit. Basically, we have this recursion tree, and only the top layer goes on chain. So we can do a lot of funky stuff in the non-top layer, like messing with the blow-up factor, making things, the verification more expensive and in complex built-ins. But just to in the top layer, forget about all of this. Just do very basic, simple things so that the verifier would work less, and then the on-chain would have less work. So like kind of get best of both worlds.
Yeah, let me also, and if you have any final questions, please now file them because we're soon wrapping up. Let me give another view on what is said here. So when dealing with complex logic, in other proof systems and other academic papers and implementations, actually two very nice things are done, and this is a third. So one is having this is about various setups. So one is taking a circuit and baking it into the proving and verification keys. So this is something that, for instance, is done a lot in the Groth 16 world, and it even involves a trusted setup, which is a bit problematic. So you can take arbitrary logic and basically work very hard to get some cryptographic key that supports that very particular thing. Another thing that you have is to have this transparent kind of pre-processing, which in papers of Alessandro Chiesa and others, it is called holographic systems. So you can take basically information about a complex computation or a circuit and write it down and get like a low degree extension of this thing as a polynomial, commit to it, everyone knows it, and then you refer to it. What is done here with recursion is a third version that is very much what we all do when we use code, which is you take your complex logic, you write it as a program, and actually this program in a von Neumann architecture goes into the memory. So this is just part of the memory, and it is then consumed. And when it's down in the recursion, this arbitrary logic has very minimal effect on verifying higher up, because it's yet another program that is executed by this virtual machine that is a Turing universal machine that is Cairo. So with this, I think we can wrap up. I see there are no more questions. So I want to thank again Shahar Samocha and Shahar Papini, and all of you who took this time to join us in this tumultuous week where everyone's basically looking at Twitter and following what's going on with this amazing implosion. We do that half of the time, but like the other 90% of the time, we're working very hard to continue delivering on what we know is the future and the right way to also prevent those kinds of shenanigans from happening. So thank you very much, and I hope to see you on our next Stark at Home in a few weeks.
Bye, guys. Thank you very much.
Thank you.